Hey guys, welcome. This is Miss Dyer, and this is the screencast for Chapter 5, Population Biology. You should have out, before the screencast, you should have out your population biology notes, and any questions that you have in this chapter, remember that you can find it in Chapter 5 of your textbook. So we're going to get started today, and before we actually jump into the notes, I would like you to answer these 3 questions. So at this time, I want you to pause the recording, and I want you to, on the top right-hand corner, answer these 3 questions in your notes, because we're going to refer back to these examples throughout the lecture. So pause right now. Okay guys, nice job. So if you have these 3 answers, we're going to use these examples as we go through your notes. And I'm going to share with you the example that I chose. So for number 1, an organism that's native to this area, I chose to go with the native white-tailed deer population. For number 2, when I thought about this population and how it might grow in size, I came up with 3 different answers. I thought about, well, obviously births. So the more white-tailed deer that are born, the larger the population. I also thought about if there are increased resources, meaning that if there's an increased amount of food supply or an increased amount of area that those deer can roam in. And I also thought about the third one, if we release some of the selective pressures, meaning maybe if predation in the area decreased or if hunting in the area decreased, we'd have a larger population of deer. For number 3, I thought about those same 3 things, but I kind of flipped them on their head. So things that would decrease the population in size would be deaths in a population. Those deaths might be associated with just normal deaths or maybe a disease that goes through the herd. There's a virus that goes through deer that's actually called chronic wasting syndrome, so perhaps that would attribute to some of the deaths. Also, I thought about resources. So maybe if we as humans overdevelop our land or if we cut off the habitat for the deer, then that would be a decreased resource, thus decreasing the population size. And the third thing I thought about would be selective pressure. So maybe if the predators in an area, so for example, maybe black bears or some of the native fox or wolf species that we have in the area might increase the predation of the white-tailed deer, as well as hunting. So if hunting increased, obviously the population would decrease. So you can think about population size is tied to how many births and how many deaths, the amount of resources in the area, and how many selective pressures are working against that population. So keep your organism in your head because we're going to be referring back to it a couple times throughout this presentation. So let's jump into things. Population growth is kind of attributed by 3 different factors. The first one, of course, is the number of births. And we say that the number of births in a population can be summarized in the birth rate. That'd be number of births. So that would be the number of births in a population divided by the number of organisms in that population. It's also contributed by the number of deaths. So the death rate, which would be the number of deaths divided by the total number of the population. Population growth is also affected by immigration and immigration, which is very confusing when you hear them spoken, but looking at them on paper, immigration is going to be individuals that leave, and immigration is going to be individuals that enter a population. So you can remember that E stands for exit, and that's going to be individuals leaving, whereas I stands for in, and that's going to be individuals coming into a population. So if you think about your species, think about how your organisms might increase due to immigration and emigration. And I thought about different herds of white-tailed deer that might leave across the Pennsylvania borderline into Maryland. So there are different groups of deer that might come into or leave the population through immigration and immigration. Okay? Now, there are 2 different types of population growth, and this is super, super important for the Keystone, guys, because these graphs are ones that you're going to need to know, and there'll probably be questions on them. So there are 2 types of growth, exponential growth and logistic growth. The first one we're looking at is exponential growth, and in math class you might have learned about exponents. Remember that they are the little superscripts above a number that tells you how many times to multiply that number by itself. And if you remember exponential growth, if you take 2 to the second, that's going to be 4. If you take 2 to the third, that's going to increase exponentially, and it's going to be 8. And 2 to the fourth is going to be 64. So an exponential growth is going to increase really, really rapidly. And this is represented by populations that have ideal conditions. And this is super important. So underline this, make a note of this in your notes. That ideal conditions means that you have unlimited resources, meaning as much space as you want, as much food as you want, no selective pressure like predators. So you will only ever have exponential growth when you are in ideal conditions for that population. So an example of my population, my white-tailed deer example, would be perhaps this population would be under exponential growth if we would prohibit hunting for a year. We would turn all of our property back into wild game land so that they could have free run, and if we would destroy all of the infrastructure of highways and roads so that all of the deer could go wherever they wanted and leave and enter populations exponentially. So that would be an example of my population in exponential growth. So pause the video here and take a moment to think about what would your population be, or what would it look like if it would experience population growth, exponential growth. Okay, so a graphic representation of what exponential growth looks like is this graph. So here we have the age of the population, and this happens to be, if you notice, in hours. So perhaps this would not be a white-tailed deer population, because I don't know many white-tailed deer that can reproduce and then further reproduce in a matter of hours. So this would most likely be an exponential growth graph for bacteria. And here we have number of organisms on our y-axis and the age of a population on our x. So if you look at the first hour, we have a little bit of an increase in the population, but not by much. By the third hour, we have doubled the population number, so it definitely has increased significantly. And if you look further from that, it doubles each time, which means this part of our graph, whatever population we are looking at, which we're assuming it's bacteria, it is experiencing ideal conditions, meaning unlimited area for growth, unlimited resources, plenty of food. And we represent this with what's called an exponential graph. So you'll see this steep, sharp incline of the population. So that's exponential growth. The opposite of that is called logistic growth. So logistic growth is when a population is no longer going to be growing. In fact, the population is going to slow or stop. Usually logistic growth comes right after exponential growth, which means we grow and grow and grow and grow, and eventually we have to slow down, and that's going to be logistic growth. What this means is logistic growth is caused by what we call limiting factors. So maybe a decreased amount of area or space, decreased food source, maybe an increase of predation, or maybe the introduction of some sort of disease to the population would all attribute to logistic growth. Logistic growth helps establish this thing called a carrying capacity. If you have a highlighter with you, highlight this sucker, because this is an important vocab term. Carrying capacity is the maximum number of excuse me. Carrying capacity is the maximum number of individuals in a population that the environment can actually support. So in this graph of logistic growth, you can see the carrying capacity, excuse me, the carrying capacity comes after a period of logistic and exponential growth. So here, if you follow along the line with me, this area would all be an example of exponential growth. And right about here, you can see that the population slows down and we start to experience logistic growth. That means that there was some sort of limiting factor that slowed the population growth down. And this area right here where the graph levels off would be our carrying capacity. That would be the maximum number of individuals in this population. So remember, this graph shows exponential growth from here to about hour 12. And as soon as that graph starts to slow down and stop, that's logistic growth and showing us carrying capacity. And the way that you measure carrying capacity is you follow the population over and you see what is the maximum number that we could have in an area. And it looks like that's about 650 organisms for this graph. Okay, so let's sum up what we know so far with a few questions. If you imagine a small island that has a population of 5 rabbits, how much might each one of the following factors affect the rabbit population? So I'm going to put these up here, and then you should pause the video and you should look through each of these different examples and figure out how each one of climate, food supply, and predation would affect them. So pause right now. Okay, so if we go through each one of these, climates would affect the rabbit population. So if we have 5 rabbits on an island, all 5 of them are going to be affected by climate. It doesn't matter that there are only 5 of them, they're all going to experience the same temperature and rainfall shift. If the food supply changes, it's going to affect 5 rabbits a little bit less because there's only 5 of them. So if we have an increase in food, those 5 rabbits will have more food. If we have a decrease in food for an island, probably won't affect 5 rabbits that much because there's only 5 of them to feed. Predation would affect 5 rabbits a little bit less as well. If there's only 5 rabbits on the island, there's going to be less of them, which means that they can hide a little bit better. So we're going to do the exact same thing, but we're going to imagine it that it's a small island that has a population of 500 rabbits. So go through the same 3 things and talk about the differences on how it would affect this population. So pause your video now. So if we look at this the small island that has 5 rabbits versus the small island that has 500 rabbits, we can go through climate, food supply, and predation, and we can see some pretty drastic differences. First of all, climate, no difference. If there's a tornado on an island that has 5 rabbits and a tornado on an island that has 500 rabbits, they are all going to suffer the same amount. However, if the food supply is different on a small island with 5 rabbits, it's going to affect the population with 500 rabbits a lot more. Meaning, if you have 500 hungry rabbits and a decreased amount of food for those 500 rabbits, it's going to significantly increase the effect on that population. So food supply is something that affects different sized populations differently, whereas climate would affect any sized population, and that's important for our next topic. The third thing, predation. If we look at a small island with 5 rabbits, those 5 rabbits would be able to hide pretty well. But if you have 500 rabbits on a small island, it means that predation is going to have a greater effect on that population. More of those 500 rabbits are going to get caught and eaten by predators than the island with 5 rabbits. So again, predation and food supply, it matters what size the population is, whereas climate will affect them all equally. All right? So number 3 says, which of these factors depend on population size? And the answer to that is that the food supply and predation are affected by population size, whereas climate does not. Okay, so what factors do not depend on population size? Climate does not depend on population size. So we summarize those things into things that are called limiting factors, which are things that decrease population size. So they decrease population growth. And examples of limiting factors would be things like competition, disease, predation, and parasitism. And we lump these things into what are called density-dependent limiting factors and density-independent limiting factors. And you do need to add those 2 terms to your notes. So they are not in your notes. You need to add density-dependent. So if you break that word down, we creative biologists named it exactly what it is. It is dependent on the density. So these are limiting factors that depend on the density of the population. So competition will increase if a population increases. Disease, if you think about it, is always found more commonly in cities than it is in rural areas because disease spreads when it is contagious in larger populations easier. So disease is density dependent. Predation will also increase if a population increases. So if you have a lot of rabbits on an island, more predators will move into the area to eat those rabbits. And parasitism will also increase. So similar to disease, more parasites will move into an area if you have a large population. Competition is not just competition for space, it's competition for any resource, and this is density dependent. So more people in an area, more competition. So food, space, water, sunlight, mates, etc. So usually there are only 3 different outcomes of competition. Either one organism will go extinct and the other one will live. One organism will make a different adaptation, so it will envelop a new niche, or one organism will leave, whereas the other organism will stay. So competition leads to either extinction, adaptation, or immigration. Predation is another density-dependent factor. So this is going to be hunting, killing, and eating an animal. And examples of these are eagles and mice. Predation is going to be a limiting factor for the prey population, while food availability is the limiting factor for the predator. So if you kind of have to think of what perspective you're looking at the problem. Predators usually kill the old, the weak, and the young. So predation is actually useful for a species in that it helps the prey population stay near a carrying capacity. And you can kind of rewind back in the presentation to remember what carrying capacity is. One example that you will absolutely need to know for the keystone, and I can almost bet each and every one of you $1 that you're going to have a question on this, is the moose and wolf population on the Lake Superior Island in the United States. So what happened is that there's an island off of the coast of Lake Superior. And what scientists have done is since the 1950s, we've put trackers on the moose and the wolf population, and we've studied them in great detail. Now, the island is isolated enough that moose and wolf cannot move on or off the island. So it means that we have an isolated population of both moose and wolves. And obviously, wolves are the predator and moose are the prey. The interesting thing is that we can see these two populations and how they interact with each other. So here in the blue line, we have the wolf population, and you should be making notes on your graph that you have in your notes on the right-hand side of your paper, that the wolf population is in blue. And you can see in the 1950s, we started out with a wolf population that was relatively stable, but there were more wolves than there were moose. And if you look at that, the wolves eventually and the moose went through a really rough winter, and that's when both of the populations decreased. Following that rough winter, we saw the wolf population actually increase. So right about here, the wolf population increased. If you think about it, if you have a lot of predators and only a certain amount of prey, those predators are going to overkill the moose. So what happened is that those wolves ran out of food. And as soon as the wolf population decreased, look at what spiked up, the moose population. So as soon as you get rid of predators, the prey are able to increase and to live a little bit better. However, they can't last that long. So here we have the moose population, which actually increased and increased and increased. But if a prey species increases too much, they're eventually going to run out of their food. So what happened on the island is that the moose overate the grass got really, really short, and the moose started to die off. At the meantime, in the same time, the wolf population started to have easy picking. So all of a sudden during this time, all of the wolves were able to eat a lot because there were tons of moose around, and not only that, they were dying because they didn't have a food source. So as a result of that, the wolf population skyrocketed and the moose population dropped. And we can see that flip-flop going on time and time again. So closer to the 1990s, we had the moose population increase to a drastic amount, and that caused the decrease of the wolf population. But you can see right here, the most recent thing we've seen is that both the wolf and the moose population are moving back towards their carrying capacity. So we can look right around here would be the carrying capacity of moose, because it looks like the population is always trying to get back to this level. So I'd say the moose carrying capacity would probably be around 25, and the wolf carrying capacity, the moose population would probably be around a little bit less than 1,200, and the wolf carrying capacity would probably be around 25, because that would be the average amount of that population that the area and the resources of that area can support. So this is a super, super important example that you guys should look over. Another example of a density-dependent limiting factor is going to be parasitism. And this is when an organism is infected by a host, and it's usually harmful to that host. So ticks and lice, other bacteria and viruses are also parasites. So those are density-dependent factors, meaning that it matters how large the population is. But there are a couple things that it does not matter how big the population is. It will affect it regardless. So things like temperature. So it doesn't matter whether or not you have one ladybug or 10,000 ladybugs. If the temperature increases, they are all going to be affected equally. Same thing with climate and natural disasters. If you have a flood, it doesn't matter if you have 5 white-tailed deer or 500 white-tailed deer, they are all going to be affected by that flood. Okay? The last section of your notes is actually population biology in reference to human population growth. And I am going to save a lot of this to what we're going to be doing after the keystones. So the only thing I will say is that our population growth right now is increasing rapidly, but we are reaching our carrying capacity, which means right now we have over 7 billion people in the world. And it continues to grow, but we are currently in logistic growth, which means that our population is slowly starting to slow down how fast we are growing. So if you look at this graph, it's really interesting because you can see how our population has changed over time. This number is a little bit iffy because we're not exactly sure when we started our population, but the numbers that first started is we noticed an increase when we started to be able to plant and cultivate crops. So that's when agriculture began, and we saw a steep increase of the human population. Now, over the next 4,000 to 5,000 years, this population was relatively steady. The next time we saw a jump in our population was when we started to develop infrastructure for plowing and irrigation of crops. So we saw in about 3000 BC that helped our population. The interesting thing is that our population rose steadily until about this point. And you see this really steep decrease was actually caused by the bubonic plague. So enough of our population decreased in that time that we actually saw a significant population decrease. Now, since then, it's really kind of scary because we've been in exponential growth for the past 1,000 years. And that exponential growth started because of the Industrial Revolution. So this spike right here was due to the fact that we started machinery, we started to be able to produce things and manufacture things, we started coal processing, and we had a more reliable source of energy. We started to create automobiles and more carbon sources like oil drilling and natural gas drilling. So the Industrial Revolution drastically affected our population. The interesting thing is that this stops at 2000. And what we've noticed is that we are hitting logistic growth. So we will eventually slow down, but up to that point, we've been experiencing really high population growth. So I'm going to leave these two math problems on the screen. I'd like you to take a look at them. So if the population is increasing 1.4% each year, and if our population is 7 billion, how large will our population be in 1 year? Second one is saying if our population continues to grow at this rate, our population will not only double in size to 12 billion, it'll get to that point only in 51 years. You need to think about the resources, how that would affect the population and the environment that other people live in. Okay, so go ahead and pause the video and figure those out now. All right, good job. So for number one, the correct answer should be 9.8 billion people, which is crazy. And for the second one, you need to think about the size, the space, the resources, and also the medicine that we have right now, how sick we would get if we had a population that large. So the last couple examples are just ones that I'd like you to practice. So if we look at this, this is a really common graph that you might see on the keystone that shows us carrying capacity. So in this graph, they might ask you where on the graph shows you exponential growth, where shows you logistic growth. And the answer to that, excuse me, is that this area right here on your graph shows you exponential growth. So from here to here would be exponential growth. And as soon as that graph starts to slow down from here to here, this would be logistic growth. So anything here would be logistic growth. And carrying capacity would be defined by where that top line equals out. Excuse me. So on the keystones, they wouldn't give you this dotted line. They would just ask you what is the carrying capacity. And the real simple way you do that is you just find the median of where that dotted line would normally be. You follow it over, and this would read out your carrying capacity. So here's some example questions that might be from this section. All other things being equal, the size of a population will decrease if A, birth rate exceeds death rate, immigration exceeds emigration, death rate exceeds birth rate, or birth rate equals death rate. So pause your video, make your selection now. Good. So if we're looking at a population decreasing, remember birth rate for A would make population grow, so it's not A. Immigration is organisms moving in more than organisms moving out, because remember immigration is into a population, emigration is out, so it's not B. Death rate exceeds birth rate. Ooh, that's looking pretty good because death would mean population decreasing. Birth rate equals death rate. So it looks like our answer is going to be C. 3, which of the following is not an example of a density-dependent limiting factor? So remember that that's something that it matters how big the population is. So pause your video, make your selection now. So make sure that you're okay with this being not an example. So natural disaster is not going to depend on the density of that species. So the correct answer is A. This is an example of that logistic growth we were talking about. So for 8, it says what time intervals in the graph shows exponential growth. For 9, they're asking which one shows limiting factors affecting the population. So pause the video now and make your selections. So for 8, the correct answer is going to be that A and B show logistic growth. Remember that, exponential growth. Remember that's when the population is increasing over time. So the correct answer should be B. For 9, the answer is going to be C, D, and E. So it's going to be C. Answer C. And that's basically logistic growth, remember, is when limiting factors are affecting a population. So the population starts to slow down during C, it equals out during D, and E is showing you the carrying capacity. And remember, if the keystones would ask you what the carrying capacity of this graph was, you would just take this line, and this looks about where it equals out, and you would follow it over, and you would read whatever amount is right here on the y-axis. Last one. In the presence of an unlimited resource, and in the absence of disease and predation, what would probably happen to a bacterial population? So pause your video and make your selection now. Okay, so remember, typical to keystones, there are always two examples that you can throw away. This is a question on logistic and exponential growth, obviously, so C and D don't even make sense. We're not going to see extinction, and we're not going to see endangerment. They're talking about what type of growth. So logistic growth is in the presence of a limited resource that's going to slow down the population growth. In this question, they're saying in the presence of unlimited resource and in the decrease of predation, what would happen to the bacterial population? So your correct answer should be B, exponential growth. So nice job, guys. This is the end of the screencast. Make sure that if you have any questions, you ask me tomorrow.